because the main motive is to make you compatible with all these technologies, and to let you know that how important these technologies are, and there is a gap which nowhere has been taught. Okay. And this is something that industry people miss a lot amongst the students, okay, amongst the freshers particularly. Okay. 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 And if you have any doubt individually also, you can WhatsApp me related to any concept. Okay, I am always going to help you out there also. Okay, so let us just continue with this. I have started presenting or not? No, I have not started presenting. 19 एक बंदा चला गया, कौन चला गया? अंकुश सिंह. Present now. Your entire screen. Is my screen visible, students? Is the screen visible? Yeah. Okay. Okay.
Temperature range and so on. A while back, we did a very detailed and easy to follow video on this topic, and we received a lot of positive feedbacks. If you have not already watched that video, click on the link in the description, and that will take you to the Real Parse blog where you can watch the video and read the article as well. But today, I'm here at Pro Control Workshop in the north of Amsterdam. They have some very cool industrial automation projects going on, and we are going to shoot a multi-series video reviewing an actual electrical control panel for you to see what the basic components of a control panel are, how they are wired, the function of a thermostat, and so on. So in this video, we are going to review the basic of an actual control panel. And I promise you, this is not going to be just a normal review. It's going to be very in-depth and like easy to follow, and you're gonna love it, I promise. And in the next video, we are going to learn. But before we get into the video, don't forget to like valuable and easy to follow videos, since we know that many of you love job everything. And then I'll be back.
This is a control panel that is used for a system that turns wastewater into clean water. An example of wastewater could be the water that comes out of the bathroom or the toilet. This control panel controls the system that cleans this wastewater and turns it into the drinking water. Pretty cool, huh? This is a two-door control panel. As you may remember from the previous RealParse video about the basics of a control panel, we mentioned that we name control panels based on the number of doors that they have. So, you have one-door, two-door, or three-door control panel enclosures, depending on how big of a panel you have. The more equipment and devices you have, the larger the control cabinet you will need. This one that we have here is a two-door control panel. Here on the front of the panel, we have some switches that are connected to the PLC inputs and outputs. The first one says mute buzzer. This is the button that you use and press when there is an active alarm on the system. When there is an active alarm on the system, the technician, engineer, or whoever is responsible on the factory floor presses this button to acknowledge the alarm and mute the buzzer. That's why we often call this the acknowledge button as well. But you may ask, why do we need this? Why should we press this button and mute the buzzer, acknowledging the alarm? Well, first off, to state the obvious, by pressing this button when there is an active alarm, you only mute the buzzer. Muting the buzzer means the alarm is still there and is still visible on the HMI, but the buzzer has stopped sounding. But why should we mute the buzzer and make it silent? Well, the answer is simple. Because you don't want that annoying loud sound of the buzzer in your ears while you're working to resolve the issue. So, when there is an active alarm on the system and it's making that crazy loud noise, the engineer or technician can press this button to mute the buzzer, and in doing so, acknowledge that they are aware of the alarm as well. Therefore, next time that you see an alarm on the HMI, but there is no sound, it probably means that somebody has already acknowledged the alarm. Next, we have the ESD reset here, which I will get into shortly. Below this switch, we have the big red emergency shutdown push button, or the E-stop as it's often called. As the name indicates, you use this switch to shut down the whole system when there is an emergency. And by doing this, you can prevent damage being caused to the system or the people around it. As you can see, it has some guarding around it, called a shroud. This will prevent the button from being used unintentionally. Emergency stop devices are always close to where people work in order to be useful, but we have this shroud around it to prevent any unwanted use. Why? Because if someone presses this button unintentionally, the whole system will be shut down completely. Now, when you press the emergency stop switch, a red alarm indicator appears on the HMI screen. After the emergency is gone and you want to run the system again, you can press the ESD reset button, or emergency shutdown reset here to clear the alarm and the indicator on the HMI. An emergency stop switch is designed to work as a normally closed switch. That means this switch is closed in normal operation, and when it is pressed, the switch opens. Now, you may wonder why we have this emergency stop as a normally closed switch. Well, let's say that you have this as a normally open switch instead. That means the switch is open in the normal state and will be closed when it's pressed, right? Now, let's say that unaware to you, a wire that is connected to the lower part of the contact has been disconnected, and you're not aware of it. Now, what happens when there is an emergency? Well, when there's an emergency, you press the emergency stop switch. But the switch will not work. Why? Because the wire has been disconnected and you're not aware of it. You never want to put yourself in a situation like this, because this is too late and also too dangerous. So what's the solution here? Well, let's repeat the same scenario, but this time replace this normally open emergency stop switch with a normally closed switch. With this normally closed switch in the normal state, there's a 24-volt signal connected to the PLC input, giving an emergency stop healthy signal to the PLC or other safety systems. When the switch is pressed, the healthy signal will be lost. And that's how the PLC or safety system knows to shut down the whole system, right? Now imagine the switch is back to the normal mode, but this wire gets disconnected for some reason. What happens now? In this situation, the healthy signal will be lost, and the PLC sees that as someone pressing the switch, right? So it shuts down the whole system. With this emergency stop switch, if the wire connected to the switch breaks, the PLC shuts down the whole system. Yes, I know, an unwanted shutdown is not what you want when a wire break happens. But this is much better than having an emergency but not being able to shut down the system. That's why you always need to use a normally closed switch for your emergency stop. The emergency stop that I have here goes to the lock mode when it's pressed. So I press the switch, and as you can see, the switch goes back to the lock mode. Now, to unlock the switch and turn it back to the normal mode again, I can twist it like this, and the switch will get back to the normal mode again. On the back of the door, you see that the switch is wired all the way to the PLC input. This is a Beckhoff PLC. The blue wires that you see here are digital input and output signals. The white wires are analog inputs and output signals. These wires come all the way from the sensors and actuators in the field and get connected to the PLC. Of course, We only have these switches on the panel door connected to the PLC, and the rest of the sensors and actuators will be connected to the PLC once we install this control panel in the field. The emergency stop that we have on the door is connected to the PLC digital input card, as it only sends an on and off signal to the PLC input. Now, you may be curious how you should know which input on the PLC you should connect the emergency stop to. Well, this is simply done based on the wiring diagram that we have here. In a later video, I'll get into the details of the wiring diagram and show you how simple it is to read and carry out the wiring on this panel. Now, let me give you an overview of all of the important components that we have for this panel.
Class, don't be worried about the electric wiring diagram. When you will be physically present here, we will let you make the electric wiring diagram on your own for every system individually. Okay, so don't be worried about that electrical diagram. For a very specific station, you are going to draw the electric wiring diagram, pneumatic circuit diagram, the interfacing, the interconnection. So you are going to do it on your own for everything, and hands-on competency you are going to attain through that. Okay, so you don't worry about that.
And also see how they are connected. As I mentioned before, this is a Beckhoff PLC. The first module that we have for this PLC is a CPU. The CPU works as the brain of the PLC. As you can see, the CPU has a few LED indicators here, a couple of Ethernet ports, and a bunch of dip switches right here. Next, we have the input and output cards. Of these cards, those with blue wires are digital input and output cards, and those with the white wires are analog input and output cards. So you see that we use separate cards for digital and analog signals. This PLC that we have here is a unit that includes a CPU and a few input and output cards, which together make up the PLC hardware. Now, let's take a look at the wires that are connected to the PLC. These wires come all the way through the trunking, and then they are connected to these terminals here. So one end of the wires are connected to the PLC cards, and the other end is connected to these terminals. Now later, when we install this control panel in the field or the factory, the sensors will be connected to the other end of these terminals. How?
These are just simple example of your terminal blocks only. Okay.
It's very simple. First, we make some holes on the bottom of this panel, like the holes that we have here. This is called a gland plate and allows the cables to come into the panel. Then, we put them into the trunking and connect them to the other end of these terminals. Please note that I am using the term cable here instead of wire. What's the difference? Wire is a single conductor, like this, but a cable is a group of wires, like this, that is covered in a jacket. So wire and cable are different. A wire is a single conductor, but a cable is a group of wire. Very simple. Outside of the control panel, you use cables, but inside the panel, you remove the jacket and use the wires. Why? Because inside the panel, you need to label every single wire. Why labeling? You need to label each wire to be able to make them uniquely identifiable, which helps with troubleshooting if there's an issue. The wire is labeled at both ends, so you know exactly where each end terminates. Moving on, as you can see, the PLC is connected to an Ethernet switch via these cables. From the other end, the Ethernet switch is connected to these devices, which we call Communication Interface Unit, or CIU. These interface units connect to the pumps that are installed in the field, and that's how the PLC can control the pumps. So the PLC is connected to this Ethernet switch first. Then the switch is connected.
They have used Ethernet as a communication protocol. We can also use Profinet, which is also a kind of a Ethernet only, and we can also use we can use Profinet, which is normally called as PN, and Industrial Ethernet, which is called as IE. So when you are interfacing your PLC, you can see an option of PN/IE, which we will see later. Okay, so we can do communication through that also, and also we can do the communication through Profibus. There are different kind of communication protocols associated to it. Okay, we will cover it in the later sessions, but just for your knowledge, there was an example of Profinet, and here they are using Industrial Ethernet. Both are a kind of, they have their own communication protocol associated to it, but they are one or same thing.
To these interface units, and then the other end of the units are connected to the pumps. Some field devices are connected to the PLC directly via wires, and some others are connected via Ethernet cables. All right, here we also have the power supplies. The bigger one has 24 volt DC output voltage and 20 ampere, or sometimes shortened to amp or amps, output current. The small one has 12 volt DC output voltage and 10 amp output current. Both of these power supplies receive 220 volt AC as input. This bigger one gives you 24 volt DC in the output here, and the smaller one gives you 12 volt DC on the output. Now, you may ask why we have two power supplies in this control panel with different output voltage. Well, that's simply because we have some devices in the control panel that work with 24 volt DC, and some other devices that work with 12 volt DC. We use this one to power the devices that work with 24 volt DC, and this one for powering the devices that work with 12 volt DC. Wonder why the 24 volt power supply has a greater output amperage compared to the 12 volt power supply? This is because the number of devices, or the devices themselves, powered by the 24 volt power supply require more input current to operate than those powered by the 12 volt power supply. We usually size the power supplies based on the amount of current output that we need. For example, we have power supplies with 1 amp, 3 amp, 5 amp, 10 amp, and 20 amp output current. The more devices we have, the more current we need, and the bigger the power supply gets. Easy, right?
So this was an in-depth overview of the essential components that you see in an
So class, my question to you is that what is the difference between a wire, cable and a strand? Yes, Bhanu, correct. A cable contains number of. Yeah, wire is a single connector, cable is a group of wire. Okay. And what is strand? Yeah. Fiber of wire. Yes, correct, Ritik, correct, very correct. So, just tell me that we can communicate only through PLC, through IO module, or we can communicate with other things also. Can we communicate with PLC through IO modules only? Yes or no? My question, can I repeat my question? That, yeah. Twister, pair of thread. Yes, you can say that strand is just a fiber of wire, and a connection of yeah, twisting and somewhat connection, or you can say collection of strand. Without isolating them, we can create a wire out of it, and through wire we can say that when we use multiple wire, by isolating each wire we can create a cable. Okay, now my question is, I just forgot my question. Yeah, IO modules. So my question to you is, okay. So my question to you is, can we communicate with PLC only through IO modules, or we can communicate with PLC through other means also? Yes or no? Can we communicate with IO modules only? Yes or no? Kindly respond to this question. No, no, no. So we can communicate through Ethernet, industrial Ethernet or Profinet or Profibus. Yeah. Yes, we can communicate through industrial Ethernet or Profinet or Profibus also. Okay. Okay. So let us just continue with our PLC. We were here, and yeah, we were here with hardware. We had completed the hardware. Now let us just look at this. So your PLC name will be here. Okay. On this side, you will have the details. You can have, there is an MLFB number that is associated to every product. You can have the detail here. Here you can see your IO status indicators. So these green LEDs will lighten up or will be switched off as per the status of your input. This is your run or stop mode. This is your error mode, and this is your maintenance mode. These are the three modes in which your PLC can run. Okay. Then you have expansion slot for signal modules. So you can add your signal module, or you can say your particular IO module here. So you have an exception slot for this here, and your CPU name and PLC type. So you can see AC, DC relay. So power supply will be AC, input will be DC, and your output will be relay type. Okay. These are the specification for your S7-1200 PLC hardware. Now you can see here, and when you will open this, when you are going to open this, you are going to see something like this. Okay. So now you can see that here, since it is an AC power supply, so you will provide your AC wiring here. The power supply will be 230 volt for powering up the PLC here. Okay. You will have your digital input modules, and your analog modules are this one. Okay. So your analog input will be fed here, and your digital module will be fed here. Okay. Then you have expansion slot for communication module here. This is your MAC address where your communication is going to be done. Okay. And this is your digital output module. So these are your digital output. This is your digital input. These are your analog input. So you have two slots for analog input also, apart from digital. Okay. But that supply will be again DC. And your power supply in 230 volt AC for powering up the PLC. This one. Okay. Now this is your 24 volt DC out from SMPS. Okay. So here what happened was that it is an AC DC relay. So your supply was AC, but you need to provide 24 volt. So from internal SMPS, your 24 volt will be out. Okay. Now you have SS door for single module. You can also add some module of signal, and you can add by accessing this. Okay. So when you open this, you have a slot for adding it. Okay. Then this is the link for your TX RX indicator. These are the indication of your communication. This is your Profinet port where you had a specific MAC address that is associated to each and every PLC. Okay, this is your again digital output module, and this is analog output connected here. So you can connect your analog input here and you can connect your analog output slots here. Now, this was an example of your AC-DC relay, and this is the photograph that we have, the photograph of the PLC that is available in mechatronics lab. Okay, so this is your CPU 1214 DC. Okay, so the supply here, you can see there was AC-DC relay, so you had a supply of 24 volt. Oh, sorry, 230 volt here. Okay, or you can say 220. But this is a DC. You can see that directly 24 volt is embedded. Okay, so this 24 volt is applied. Okay, and the current consumption is 1.28 and IP is 20. So I told you about IP. What is IP class? Can you do you memorize what I told you about IP? Do you know what is IP? Something related to? I remember I have written it on the chat box also. Full form of IP. Yeah, it is your ingress protocol. What is IP rating, Ritik? Can you please elaborate it? Yeah, ingress protocol. Yes, very correct. It is your ingress protocol. Yes. So, yeah, it is your ingress protocol. Okay, we have already, yeah. So, what kind of, you can say, water atmosphere it can handle, and what kind of solid particle atmosphere it can handle. So here the IP rating is 20. So it cannot handle any kind of moisture. Okay, but to the level of 2, I think 2 will be of 9 some millimeters dust particle it can handle. Okay, so there are specification. The first number is associated to your solid particles and second number is associated with your water particles or your water. So if it is 0, so it cannot handle any kind of water presence around it. Okay. This is your SMPS that is available with us. Okay, you can see that AC input can be 100 to 240 volt AC, and DC input, you can say range, or you can say DC output range, it is not input range, 95 volt to 250 volt we can apply. Sorry, yeah, DC range we can also apply. For AC it will be converting it into DC, and for DC it can just step down it. Okay, amperage is 4.2. Kindly remember this amperage is very much important. We have already learned from the video that amperage is also important. So apart from 24 volt 100 watt, the amperage is also important, which is 4.2 ampere. Okay, the AC frequency is 45 to 65 hertz that it can handle. Okay, so now you can see there are 3 wires here. So one is green, one is red, one is black. Here your color code is black is for neutral, red is for line, and green is for your earth. Okay, and this is being converted into your 24 volt. So red is your positive and black is your negative. Then you have MCB, you have 4 ampere double pole MCB. Tripping characteristic is C and D. So tripping characteristics are also associated with your electrical engineering. We will cover it separately when you will be present here. A very brief introduction to just tripping characteristics. There is nothing about tripping characteristic. Much more detail is not useful for you, but for a very brief understanding that what kind of current. So the rated current is 4 ampere. That doesn't mean that it will shut down only on 4 ampere. it can handle a larger amount of amperage, and it will not just trip at 4 ampere. That depends on tripping characteristics also. Okay, we will go into that particular detail, but you know MCB, that if the amperage is more than a rated current, or not rated current, the current that it can handle, it will trip. Okay, so now you can see that red line is coming from here, positive and negative and positive and negative. This is a double pole MCB. Then you can see this input wiring. Okay, I have opened this particular slot now. This slot I have opened, and now you can see that this is your 24 volt. Okay, this is your line. This is your common negative black wire. Okay, and these are your output. So this is your I 0.0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. Then 1.0, 1.1, 1.2, 1.3, 1.4, 1.5. Okay, so why we have not taken 0.8? Can anyone tell me? Can anyone tell me that why we have not taken 0.8? From 0.7 we have taken 1.0. Why we have not taken 0.8? Can anyone tell me? Okay, so do you know a little bit about bit, byte, word, double word? A little bit knowledge about that? Do you know about it? What is a bit? What is a byte? What is the difference between bit, byte, and word? Do you know about it? Class, kindly respond on the chat box. Yeah, you know about bit, byte, word, double word. Yeah, you know about it. Okay, so now can you answer that why it is 0.7 and then it start from 1.0? Why not 0.8? Now can you answer? Even if it is incorrect. Yes, Banu, 0278. Yes. So for one byte instruction, they have completed one byte. So we address bits as per a particular byte also. So our addressing is like that only. So for after completion of one byte, we move to another byte. So from 0 byte to 1 byte when we have shifted. So for particular 0 byte, we had 0, 1, 2, 3, 4, 5, 6, 7, 8 bits for 0 byte, and then for 1 byte we have another. Okay, yeah, so now you can see this connection here. So you can see that 0, 1, 2, 3, 4, 5, 7, and then we have 0, 1, 2, 3. We also have analog inputs available with us. Okay, so we have two analog inputs also available with us of DC, DC, DC. Okay, now this is output wiring. Again, you have 24 volt supply, 0 volt supply, and then you have your common, and then you have your 0.0, 0.1, 0.2, 0.3, and you have 7 outputs for this particular PLC. Okay, so this is how it can be wired. Okay, the internal wiring for AC particularly, you can see that now what it is doing is that you can see that we have seen the example of this particular AC also. This is AC. Okay, now you can see the wiring also. So we will have something in common. Okay, so this is your common. Okay, now you can see that your supply was given, you had grounded it. Okay, then you had DC in common. This is positive, and this common is being now converted into this. So now you can see or you can just interpret that this circuit is going to get completed how. Just have a very quick view here. Let me use a red color pen. You will have an optical isolator. Okay, here. This will be your optical isolator that will be providing your current to the CPU. Okay, okay. And this will be your transistor. Okay, this is your optical, and now you can see that current is passing from this. When the circuit is completed, the current is passing from this and current is flowing in this particular direction. Okay, so if you have a sensor, okay, this connection is going to get completed, closed. And now you know that the current is flowing into the digital input block of the PLC. Okay, so current is flowing into the PLC. Okay, so what kind of PLC this will be? Will it be sourcing or syncing? Will it be sourcing or syncing? Current is flowing into the PLC. Yes, it will be syncing. And for syncing type of PLC, we are going to attach what kind of sensor to it? PNP or LPN? PNP. Yeah, so I think you are aligned to it. Now you know the circuit also. Now. Yeah. So you know about sourcing and syncing. You know about how PLC works for sourcing and syncing. You also know that why 0 to 4 to 20 milliamp is required, and why not 0 to 20 milliamperes is required. Now let us switch on to addressing of input also. Okay. So as we have seen, the address was, you can see here that these addresses are I0.1, 0.0. So what kind of addressing is required for PLC? Let us just have a very quick and yeah, we will conclude the session after addressing. We have much time for that. Yeah, so addressing. So you will first have your identifiers, then you will have your byte numbers, and then you will have your bit number. Okay, so we have already seen that it will be 0, .1, .2, .3, .4, .5, .6, .7. Then it will be 1, .0, .1, .2, .3, .4, .5, .6, .7, etc. Okay, your identifier will be this. I will be your input, Q will be your output, M will be your memory. Okay, so for a particular IB0, okay, 8th number will be I0.7, 7th will be I0.6, first one will be I0.0. So it will work like this only: 0.0, 0.1, 0.2, 0.3, 0.4. Okay, from right to left. So you need your addressing like this for bit address. Okay, 0.0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. So now can you address these? Let us say this is your A, this is your A, this is your B. Kindly answer the address to me on the WhatsApp group. Okay, A, B, C, D, E and F. Okay, so what will be the address of this X, this A, B, C, D, E and F? Okay, quickly just answer me this. What will be the address? I need a complete address like I10 dot I1.0, I1.2, like this. Okay, for each and every example, kindly respond me on WhatsApp. Let me just repeat the addressing. It will be something like this: I0.7. Okay, so for this particular example, this is 1 and this is 6, and this is I only. Okay, input only. So this will be I1.6. A will be I1.6, B will be Q2.5. Yes, C will be 0.4, D will be Q0.3. Okay, I2.1. Yeah, correct. I1.6, Q0.5. Sahil, you are correct. Good. Ritik, you are also correct. Good. Muskan, your answer is 1.6 to 1.5, I0.4 to 0.6, I2.1, BQ1.0. Yes, correct. Very good, Muskan. Adarsh, I1.6, Q2.5, I0.4, Q0.3, I2.1. Yes, correct. Adarsh, very good. Sunidhi, yeah, 1.6, correct. Q2.5, correct. I0.4, correct. Q0.3, correct. I2.1, yes, correct. Sunidhi, you are also correct. I1.6, Q2.5, 0.4, 0.3, 2.1, 1.0, yes, correct. Abhay, you are also correct. Bhanu, you are also correct. Yes, good, Bhanu. Shubham, you are. Yes, Shubham, you are also correct. Varun is also correct. He has used Q. Yeah, Nandini, you are also correct. 106 user. Yes, correct. Kalpana, you are also correct. Nayan. Oh wow, Nayan has made on the entire table for us. Thank you, Nayan. Thank you very much. 0.01. Yes. And you can refer to the table that Nayan has made. Good. Prachita, you are also correct. And Hitender, you are also correct. Yeah, Q 1.0, 0.4. Yes, so I think all of us are correct. A, B, C, D, E, F. Yes, Alok, you are also correct. And Khush, you are also, Khushbu, yes, you are also correct. Yeah, so all of you are correct. I think we all are aligned to this. The solution is this only: I1.6, Q2.5, I0.4, Q0.3, I2.1, Q1.0. Yes, correct. So the solution is correct. Now we know that for memory concept, we know that from 0.0 to 0.1, we will have individual bits, and then from one bit, we will have a one byte. Okay, so for M 0.0, then we can have an address of MB0. Okay, and if there are two words, the two byte will connect you with a MW0. So if you are going to address one bit memory, then you can address M0.0 to M0.7 and vice versa. Okay, so from 1 to 7 you can add. Okay, but when you are going to address a particular byte into a memory, then you will use MB0. Okay, which will be a combination of this. Okay, then if you want to address a word, then you will use MW0. Okay, so for example, this can be only for switching or one single logic. Okay, but you can have a parameter where you need to define the temperature of fraction or something like that, then you will need a byte in a memory bit and a word in a memory bit, or most probably a double word also. Okay, so for 8 byte you can have, for 1 byte you can have 8 bits. Similarly, you can have 16 bit for this. Okay, so 2 to the power 16 solutions you can have, permutations you can have, and you can have 2 to the power 32 in your double word. Okay, so from bit to byte to word to double word, your address will be M, MB, MW, MD. Okay, then you can have Boolean type data. Then it will be a 1-bit data storage will be like M0.0. Then you can have byte, you will have 8 bits data. It can have memory byte, MB1. Then you can have integers are normally considered to be stored in memory word, which is MW2. Okay, then you have double integers, which is 32-bit data, which is MD4. Okay, you can denote it like double memory word MD4, and real numbers are also 32.0. You can use a double memory word for it. Okay, so like MD8, etc. Okay, data type again, bit is Boolean 0 or 1. Your byte can be 0 to 255, so you can have 2 to the power 8 minus 1 because 0 is added. Okay, so as integer, single short integer can be 255, 256 only, but 0 to 127 here, and negative minus 128 at the another side. U integer is unsigned integer with 16 bit, so you can have 2 to the power 16, so 0 to 2 to the power 16 minus 1, 65535. Okay, then you can have 16-bit signed integer. This can be divided. Okay, so this will be 3278, and here will be 0, so 32767 also. And you can have U identified also. This will be of 2 to the power 32 bits. Okay, then D integer, which is your signed double integer, same like this. Your bifurcation will be like this only. Okay, for real time you have 32 dot, for floating point 3.44 into 10 to the power 38 to 1.157 10 to the power minus 38. So you will again have for floating type also, just like negative integers. For negative you had one single address. For here you can have 2 to the power minus 1, etc. 2 to the power minus 2, etc. Okay, so this is how floating can be done. You can have string with 2 byte to 255 byte. Okay, it can be user defined. And then we have TIA, so software introduction in next session. Okay, so I would like to conclude the session for today. What we have learned is about the basics of PLC. Okay, and what we have learned was about electrical panel, about PLC, what is a PLC, how a PLC is connected. Okay, what are the addresses that can be given to a particular PLC. So for tomorrow exercise, you have a exercise that you need to install TIA portal. We will give you a brief about TIA portal tomorrow. Okay, class, is that fine? So, and about your attendance, don't just let me take your attendance first. Stop presenting. So there are 18, 17 students are only there. Oh, Abhay is there, Adarsh. There were 21 students in the middle of the session. Now there are only 2 students are not present. Just let me take the attendance. And if they are off because of some network issue, kindly ask them to communicate it to me individually, not on the group, because on the group there are my center head also. He might ask question that why it happened. Okay, you can individually message me if there is any issue. Meanwhile, just let me take your attendance first. I have your trainer list. Yeah. Yes, kindly unmute yourself, or you can also mark your attendance through chat box also. Just let me